So first thing, most important thing maybe, we are in week 17, finals next week. Check out the final info page for more information. We are just going to review for both lectures this week. That is my plan at least. And two things. Remember that I accept late labs, iBook assignments, check-in surveys up until the last day of classes. That's Friday, a minute before midnight. So get things in by then. Also for Zybooks assignments, if you turn those in late, you have to tell me so that I can manually change your grade to half credit. So just remember to do that by Friday at midnight. And then also, your Zybook is not a physical book. It expires, sadly. Go to each chapter and click Save as PDF or Print or whatever the button is. If you haven't found it yet, I can show it to you. But make sure to get that because it's probably going to expire sometime over winter break. And then you'll lose it forever. And it's a good book, so keep it. Yeah, that is all my logistical things. Are we good to get started with the review? And you can stop me at any point. This is just for you guys, so this is just what I chose to write down. But everything can be changed. So step one, as usual, I've made you all a beautiful cheat sheet that I will be giving you later. Here it is. It's got pointer stuff, which we'll talk about. Recursion stuff, just some ideas about how to solve the problem. Beautiful and color-coded as usual. You are welcome. Information about exceptions, how those work, some bitwise operations, stuff, make files, and I think that's it. Cool. So yeah, I'll give this to you after this class. You'll be able to click on it and enjoy it. And we'll come back to it as we talk about things, I think. So yeah, the first, I think today, let's talk about older stuff that this class is just built on top of, right? Stuff from previous midterms that I don't want you to forget. Let's talk about that today, and then we'll talk about newer stuff next time. And that sounds like the plan. So let's first talk about references. Okay, so let's see here. A reference, remember how to make it, remember the syntax, remember what it does. So a reference is it's an alias for another variable. It's a way to give an existing variable another name. So for example, if you wanted to do this inside of a function, which usually you don't, you could do it like this. Int x equals 42. That would make the box in memory. That's just a normal local variable x holding 42. To make a reference, it's the ampersand next to the type. Int ampersand y. Let me draw a better ampersand. Ampersand y equals x. And this starts off the reference, and it gives this box another name. Now you could say x plus plus, y plus plus. It all works out. Okay? That is the goal for references. And yeah, does that make enough sense? Usually you're going to use these with parameters because you want to not copy memory, but you can totally do it in the body of a function, just like this. So yeah, we like to use references for two main reasons. First of all, we want to be able to access somebody else's memory, maybe across function calls. References are good for that. A reference parameter, pass by reference, call by reference. Then also, you're not copying anything. If I were to say int z equals x, this is a brand new variable z that holds a copy of x. Okay, that is maybe not what you want. You can imagine maybe you had a giant vector or something. You don't want to copy that. Okay, you don't want to copy it if you had a giant vector. If it's got a bunch of numbers inside of it. You don't want to pass this and make two giant vectors. You'd like to just give a new name, like v and, I don't know, v2. Give a new name to the existing one. Don't recopy those million elements. I guess that's what references are good for, so let's get some examples of those. Where do I want to be? Let's be here. Right folder yet. What lecture are we? This is lecture 30. There. And references.cpp. So let's do first example. Swapping some ints. So we'll make our lovely swap functions. Here's how we'll do it. We'll have int a equals 42, int b equals 43, and we'll swap them the wrong way, swap by value, which just involves making copies a and b, and we'll print out a and b. And then we'll do it the right way. We'll do swap by reference. That takes the parameters by reference. And so it really has access to a and b now. Alright, so let's do both of these. So swap by value will look like this. It's a void function. It takes two things. Let's call them x and y instead of a and b. Int x, int y. And remember how to swap stuff, right? So int temp equals one of them. That one equals the other one. And that last one equals temp. That's how you swap stuff. And this isn't going to work because x and y are copies. They're just brand new variables with the same values as a and b, 42 and 43. We're going to swap x and y, but we're not touching a and b. Remember that problem? That is the issue with copying things, with passing things by value. If we really want to change stuff, we'll pass them by reference. We'll say int reference x, int reference y. And so now when these get initialized, x will be set to a reference to a. Y will be set to a reference to b. And that means same box in memory, just a new name. I can actually touch the stuff. When I set x and y, I'm really setting a and b. Okay? So the first time, a and b, nothing happens. So there's still 42 and 43 after swap by value because we just made copies. That's what passing without references or pointers does. And then when we swap by reference, we're actually making, we're giving new names to those existing variables, and so we're allowed to touch them inside of this function. And it really did get it swapped to 43 and 42. Yay. Any questions about that? Is it all coming back to us? So don't forget about your references. Another example, let's make a very large vector. Let's make it like, size 1000. Let's have it hold 1042s. We would like to be able to pass this. Let's make like a sum function, sum all the elements in a vector function. We'd like to pass this giant vector that we're going to make in main to our function and have it not like copy it, because maybe we'll run out of memory if we have to make another copy of this size 1000. I'd like to just keep the same one, just touch it, get its stuff, okay, without copying. So let's make a vector. Here's a quick way you can use one of the vector's constructors. It's called a fill constructor. You can say v1042. This makes a vector. V is now a vector holding 1000 elements, all set to 42. That's an easy way to fill up a vector with a bunch of stuff, the same stuff. And we'd like to sum all the elements in V. So let's make a sum function. And let's have this vector, this giant vector, could be a size of 1,000,000. Let's make that pass by reference so that we're not going to waste memory trying to copy it just to sum every element. Let's reuse that vector. Okay, int sum, vector int reference, call it v again. So right now I'm allowed to change v. It's nice because I'm not copying it, but I could do this. I could touch main's v, right? I could set v of 0 to something to disallow that, to just get the reuse so that we can not copy things, not copying stuff. You can say const reference. This lets us not copy it when we get past our vector, but we will also be forced to not change it. Something interesting is going on out there. Some sort of press conference, it looked like. I wonder what that is. Okay, so constant reference, no copying, good. And also no touching the non-copied value. So int, let's build up a sum variable. I'll call it int res for result. I'm eventually going to return that. And let's go through every element of v. Res plus equals I. So that will have my summed value, and in theory it's going to be 42,000, right? Because there's 1,042s in this vector. And it's much nicer. It takes much less time because there's no copying, and it sums everybody. So use constant references as much as you possibly can. That is what I wanted to say. Any questions about that example? All right, so let's see, what do I want to do next? Yeah. Next example, this is going to be a complicated one, it'll be fun. Let us review classes and methods. So what is a class but just a little box that has stuff inside of it? So classes are a way to like make your own type, and every element of that type, every object, can have a bunch of member variables associated with it that belong to it, and a bunch of member functions, things that you can ask it to do. Like a member function or a method is like a message that you can pass to your object, like you're talking to it. Okay? So, yeah, you make objects of a class, and you can talk to those objects by sending them messages. That's the metaphor. You treat them like they're real-life things that you can touch. All right? So, let's see. First example. Let us make a stopwatch class. It'll be cute. We'll use ctime, and we will just keep track of how long something has been going on. We'll start our little stopwatch and have it like keep time for us. So we'll just have a program that keeps on outputting how long it's been since the program started. It just starts counting. So we'll use the ctime library for that. Let's do it this way. I hope this works again, because I need to show you ctime. C library, ctime. This was down earlier today. So if I click this, will it load is the question. It will not. So it's so sad, our documentation website is down right now. ctime. We'll have to use the competing cppreference.com this time. Alas. So ctime header. What that allows us to do is call the clock function, and I can subtract things when I call the clock function. They give me back clock t's. Subtracting clock t's gives me some number, some weird looking number, and to convert that to actual time, I can divide by this constant clocks per sec. So let me just show you that. It'll make more sense when I do it. Stopwatch.cpp. I want to include ctime. And this also lets me show you a cool feature that maybe you haven't seen, a new escape character. So I'd like to make like a stopwatch s object s.start. Oops, s.start. Start my little stopwatch. Start it ticking, and then until the end of time, see out how much time. Like look at the stopwatch. Get time elapsed. We'll say. This will be fun. We'll use an endl to start though. So let's make this class that has the ability to keep track of time. So class stopwatch. What does it need? Well, public. Let's not even give it a constructor. Private. It needs to hold on to the starting time. The starting time when we call clock, which gives us back a clock t. So let's save that. Clock t starting time, and it's the start function that's going to set that. Essentially the constructor. So void start. And then we'll have another method that gives us the number of seconds that have elapsed since we called that start function. double, because we might have a fractional number of seconds, get time elapsed. And this will be const, because it doesn't change anything. It'll just look at the starting time. Okay, so let's implement these two methods. And it's stopwatches start method. Stopwatches get time elapsed method. So the start method just needs to set the starting time. So starting time equals, just call clock. That's legitimately all that you need to do. And that looks at the time, I guess, inside of the computer. And then to get the time elapsed, we just need to look at the clock one more time. So call clock again, get the time right now. That's a clock T. Current time equals clock, and then we would like to return current time is like a later number minus starting time over clocks per second to convert it from whatever the clock units is to actual seconds. And because this is an integer, clocks per second is an integer, this will do integer division unless we do something like this, static cast to double of just the first thing. That'll work. So now we can run our silly little program, and it'll just keep printing out the current time, how many seconds have elapsed. It takes a long time to print stuff, so it's a little bit delayed, but it's counting up. That's good enough for us. Okay? So this is making 1,000,000 lines, essentially, every second. That's no fun. Let me show you something cool. Maybe you've read about this in your book. Have you guys seen the \R? Does anybody know what the \R is? You got your \T for tab, \N for new line, \0 for null terminator character. Does anybody remember what \R is? You read about that? It's a cool one. It stands for, the R stands for return. It's short for carriage return. And now I have to talk about very, very old things. So this comes from back when you were sending data not to a terminal, but to a printer. Like your terminal was a typewriter, and you typed on paper, and that sent electrical signals to the server that you were connected to. And it sent you back the data, and it printed not to a screen, but to a printed page. Like it started typing on the page for you. And so that's how you interacted with computers back in the day. It was called a teletype. And this thing is called a carriage return. So I don't know. Here's my best drawing of a typewriter. Do we all know what a typewriter is, first of all? It was the old school way of writing stuff. So it's my typewriter. It holds the paper right here. And, I don't know, you press a key, and it whacks the paper, right? It whacks the paper with the little thing, and that makes the mark. And if you whack enough characters, right, it starts typing a line, and once you're done with the line, it dings. We all know about this. We all know how typewriters work. And so you have a little lever right here to, like, once you start typing, it starts moving the paper that way so that it can start, like, going to the rest of the line. You need to move it back once it gets to the end of the line with this lever. Okay? So you need to pull it that way, and that is called a carriage return. This thing is the carriage, and you're returning it back to the start of the line so that it can start typing on the next line for you. Okay? That is what typewriters did. Hopefully that was a good enough explanation. I'm sure there's plenty of YouTube videos if this is just too old stuff for you. But we get that still. Instead of saying endl, if I say \R, it will perform a virtual carriage return. \R character. It will perform a virtual carriage return and go back to the start of the line. And if I start giving it more stuff, like a new cout statement, it will, oh man, it will overwrite the stuff that was already there on that same line. So watch this. Recompile, rerun. It just keeps on overwriting the same line now with the \R. It moves the cursor back to the start of the line. returns the carriage to the beginning so that it can start whacking virtual keys and typing virtual characters on your virtual page. Isn't that fun? So yeah, that's what \r does. It's called a carriage return. Any questions about this example? Right. My next class example is much more complicated. I would not dream of asking you this on a test, but it's such a good example, I think. I'm excited to give it to you. So we are going to model, as a class, we're going to model a calculator. We are going to make a method for every button, like here, press the 7 key, press the 8 key, press the 5 key. And if you do it in that order, it should build up the number 785, right? Press the plus key. Then it starts waiting for the next number to type. Press the equals key to actually do the operation. Okay, we're going to make a calculator with buttons. We're going to model one of those as a class. Okay, so yeah, we have to think about what do we need? What do we need to represent the calculation in a calculator object? Like we'll call it C. What does it need inside of it? Like to actually compute like something if we type enough buttons, 42 plus 55 or something. It needs to hold on to some stuff, right? It needs to hold on to the 42. It needs to hold on to the 55. And once I press equals, it needs to actually like remember that we were trying to do a plus as well, so it can actually perform the operation at that point. So this calculator object needs to hold on to like the first operand 1, that's the 42. It needs to hold on to the second operand, the 55, and then in between we type like the plus button or the minus button. It needs to remember which operation to actually perform. Operation. If we can hold on to those three things and build them up properly every time we press a key, we have a calculator. Ooh, this will be fun. So here are the methods that we'll need. Like we'll make one for each button on the calculator. We'll make a press plus method. So we can say C.press plus, C.press minus, press times, press divide. Okay. We'll also need a button for every digit that we could possibly press on our calculator. We'll press it one at a time virtually. So we need, instead of like a press 1 button, press 2 button, press 3 button, we'll make a press digit button that takes a single digit at a time. Okay. Then we need to think about how we're going to build up a bigger number. So like if I want to build up the number 123, I have to like press digit 1, press digit 2, press digit 3, and it better like add to operand 1 the correct digit at the end as an int. Interesting. So we'll have to do that somehow. We'll have to like put that in there. And then we'll have like a press enter button or the press equal button. And that will actually look at all the stuff that we've built up and actually perform the computation and give it back. The rest of these are void. This one's int. Okay? And then we'll test it too. So that is the plan. I hope that makes enough sense. Let's get started with that. And we'll discover that we need some interesting stuff. So let's get the scaffold ready at least. Here's what I want to do. Like, I don't know. Let's build up the 42 plus 55, I guess. Calculator.cpp. What do I need? I will eventually need strings. So I'll just do that now. But here's what I want to do. I want to be able to make a calculator object. Calculator C. I want to build up these results. I want to press the 4 button, like C.press digit 4, then 2, and so that should build up the number 42, right? 42 on my screen, and then I want to add to that 55, so I'll press the plus button, C.press plus, and then I'll press 55. So I need to press the 2 digits, 5, right? 5 twice. And so this should build up the computation 42 plus 55. And then when I press enter, C.press enter, that will perform the operation and hopefully we can output it and it looks like the right answer, which is apparently 97. That's how I want to use my calculator. I hope that makes sense. So we notice that we need a few things. Let's get that started in the calculator class. We notice we need at least three member variables inside of our calculator. We need to store the 42, we need to store the plus, we need to store the 55. The plus could have been minus or times as well, though. So we need operand 1, operand 2, and the operation we're trying to perform. Okay. So operand 1, operand 2, and then we'll store the operation as, let's just use store it as a character. We'll store like the plus character if we're trying to do plus, etc. for the other ones. Okay. So we're probably going to need a constructor. That makes enough sense. We need all these press buttons. We need a void press digit function, method I mean. Press digit, int digit. We need all the operations, so void press plus, press minus, times, and divide. These will correspond to buttons on our virtual calculator. And then the last one we need is press enter. We'll separate that. Press enter, which actually performs the calculation and returns an int. Okay, so those are the things we need. At least the constructor, we can mostly get started. When we make our calculator object, like the screen's blank, it's waiting for the first number, something like that, right? So the operand 1 and operand 2, we have no clue what they are. The operation, we have no clue what it is. We can at least zero them out. So let's zero out at least the operands in our constructor. But let's get all these down here, ready to be implemented. Boop. Calculator, : calculator. There we go. Let's fill it in now. Eventually we can implement it. But there's one thing we're not really ready for yet. When we're typing, like 4, then 2, we're pressing 4, then we're pressing 2, then we press plus, and like it should know that we're ready to fill in operand 2 now instead of operand 1. Like how do you do all that? The answer is we use a state machine for our calculator. Remember that? So we need to keep track of a state because we need to be building up at the very beginning. Our start state is we're building up the first number. We're trying to type in the first number. We can be in the first number state. Does that make sense? As long as we type a digit, 0, 1, all the way to 9, we are still in the first number state. We're just building up that first number bigger and bigger because we're typing a single digit at a time. Like if you type 123, you press the buttons 1, 2, 3. You want to build up the number 123. Okay? So you're in the first number state trying to build up that number. The second you press an operation, like you press the plus, the minus, the times, or the divide, then you're ready to start typing the second operand, right? You're starting to wait for the second number now. I hope that makes sense. Second number. So you change states, and that's how our calculator will keep track of where we are in the computation. Like we need to start adding stuff to operand 2 now, as long as you type digits. 1, ... all the way to 9. As long as you type digits, you're still building up the second number. Like you type 1, then 2, then 3 to build up 123. Once you press the equal key, then you can finally, like, the calculator displays its results, and then you're back to the first number state, ready to do another computation. But that's how a calculator works. Does that make sense? You type a bunch of numbers. That's the first number. You stay in that first number, building it up as long as you're typing digits. Then you press an operation that alerts the calculator that you're ready to type the second number now. That's the new state. And you start building that up, and that should know to like modify operand 2 instead of operand 1 this time. And you type a bunch of digits to build up the second number. Once you type enter, that alerts the calculator that I'm ready to compute the final computation. I've built up the second number completely. Save the first number somewhere. Save the operation somewhere. Use that second number that I just typed to compute the result. So, yeah, we're going to use a state machine, and so we need a state variable. I'll store the state as a string. String state. And so our calculator, when we construct a calculator, the starting state is going to be operand 1 set to nothing, operand 2 set to 0 as well, just to zero it all out. The operation will change that eventually with a button press. We can leave that undefined. And then the state starts out being first number. Okay. We are in the first number state at the beginning, waiting to fill in operand 1 with a bunch of digits. Okay, that's the idea. So I guess the final piece of the puzzle is we're going to press a single digit at a time. How do we build up a number that's larger than 1 digit? Do we have any thoughts about that? So I'm going to type 1, then 2, then 3. I don't know when I'm going to stop, so we have to like build up first 1, then 12, then 123. Does that make sense? That needs to go in operand 1, essentially. Operand 1. We'll start it at 0, though. So I need this kind of thing to happen. Or I guess I started at 0, so I go from 0 to 1 to 12 to 123 if I type these digits in order. Do we see any ways to make this happen? So like I press the 1, it does this. I press the 2, it does this. I press the 3, it makes this one happen. What are our thoughts? I'm building up a number a digit at a time. Yeah, nice. Did everybody hear that? That was exactly the right answer. So if I have a number, like I have 12 already, and I just typed 3, how do I make 123 from 12? Well, first, what I can do is I can multiply this number by 10, so I can make it 120, to shift it a little bit. So multiply it by 10 first to make 120, and then I can add that new digit in. Now it'll be in the ones place, add that 3. Does that make sense? And this pattern will work for every digit. You start at 0, you can still use times 10, it's just still 0, plus the 1. That makes the 1. You type the 2 character, you press the 2 button. Multiply what you had by 10, so that makes actually 10, add 2. That makes 12. You have 12 now. Multiply by 10, add 3, that makes 123. So operand 1, if I type the 1 digit, that's times 10 plus 1, that makes 1. If I type the 2 digit, it makes 10, and then adds a 2, makes it 12. And if I type the 3 digit, it makes it 120, and then adds the 3, that makes 123. So that's how we build up our operands. And that's also why they need to start at 0. Because you want to shift the 0 away. It makes it so you can do the same thing each time. Otherwise, you have to have some weird starting value stuff. Okay. Does that process make sense? That's how you build up a bigger number 1 digit at a time. That's all we need now. Based on the current state we're in, like when we press digit, we're either filling in operand 1 or operand 2. Once we call like press plus, minus, times, or divide, we need to save the operation for later in our operation variable. And then change the state to second number now. And then as long as we're pressing digits in second number, we need to fill in operand 2. The second we press enter, we compute our answer using operand 1, operand 2 operation. And we also set the state back to first number so that we can do another operation on our calculator. Okay, so that will finally allow us to fill in all this stuff. So press enter. So, all right, when we press a digit, when we call press digit, we need to fill in the next digit in either operand 1 or operand 2. We're just pressing a digit right now. We're not sure which one we need to fill in. We need to check our state. So check our state. Are we in first number or second number? So if state is equal to first number, we want to add to operand 1. Add this digit to operand 1. Else, the state must have been second number. That's the only other option. So we'll add the number to operand 2 instead. Okay? So how do you add this digit to operand 1? You say operand 1 equals whatever it was times 10 plus that new digit. That's how you add it there. Same for operand 2. Okay, does that make sense? That's how press digit works. It's going to add that digit to wherever it should be, given the state of our calculator. We're either in the first number state or the second number state. You can keep typing things, and it will add that digit one at a time to either operand 1 or operand 2. Okay. Press plus, minus, times, and divide. You can get pretty fancy with this. You can be like, I'm not allowing you to press plus, minus, times, or divide if I'm in the second number state. So you can like check the state to make sure you're in the first number state. And then you disallow the plus otherwise. But we'll just make it easier on ourselves. We'll just assume the user's doing it right. So press plus, that will save away the operation. Like we're storing it as a char, right? So operation equals the plus operator now. We'll save that away in our member variable. And then we'll also change our state. So we just typed a non-number, an operation. So we should move to the second number state. So state is now second number. That's how plus will work. Does that make sense? Save away the operation for later and advance our state. And this is the same for all the other operations, just it's a different character. Oop. And this is minus. Okay, so we're just saving the operation for later, advancing our state, and then we'll press some more digits to fill in operand 2 now, because the state's no longer first number. And then finally, we press equals, and that performs our calculation. Or press enter, I guess. When we press enter, we have to build up a result, int result. And we're going to return that. How do we get at that result? Well, we have to use our operand 1, our operand 2, and the operation. So we just need to perform the operation. What is that? Well, we have to look at our operation character. If the operation that we're supposed to perform is a plus, then the result is equal to operand 1, which we built up, plus operand 2, which we also built up. All right? The rest is similar. Else, if the operation that we're trying to perform is equal to minus, then the result is take operand 1 and operand 2 and subtract them from each other. Yeah, that's how you do it. So just keep on doing this. I guess we can make the last one an else. If it's a multiplication operation, do that one. Otherwise, it must have been divide, so do that. So that's performing the operation. And we're going to return that result. We built up the computation correctly. The only last thing we need to do is like reset our state. So the state is now first number. We're ready to do another calculation. Like we need to clear out the display on our virtual calculator. So reset the state of the calculator. And that involves setting the state variable to first number again. And also, we should zero out the operand so that we could like fill in new digits in the next time we use the calculator. Operand 1, operand 1 equals operand 2 equals 0. So set them all to 0. Then finally, we have the result. Return that. I guess that's not really necessary. That's the same line. So that's the press enter operation or method. Does that make sense? Taking all the stuff that we built up, perform the operation, resetting our state so that we're ready to use the calculator once more with another pair of numbers and another operation. Okay? So in theory, if I did all this right, okay, question first.
Since the division is division, would you have to be able to make the result a double?
Technically, yes. We're just going to do integer division for this one. But yeah, if you wanted to get fancy, you could make operand 1 and operand 2 doubles and have like a press dot button so you can fill in a decimal number. You have to do some fancy stuff there to fill in like the 10th place, the 100th place. But yeah, we'll just hard code integer division for this simple calculator. Any other questions? So I have built up this computation. In theory, this should print, if we did it all right, it should print 97. Wow. And then we have 97. Yay. That's exciting. So that's a good start. The last thing that I want to do is just, let's write some tests so that we have some practice doing that. Let's get an assert true in here somewhere. Where is an assert true? Here's my closest assert true. Lecture 27, TDD example. Let's steal this assert true. Thank you. Put it right here. And so let's turn this into a test instead. So let's call this, I don't know, void test calculator 1. And let's turn this computation into a test that involves assert true. So instead of printing something, we will assert that when we press enter on our calculator right now, it will be equal to 97. Assert true, c.press enter, that better be equal to 97. That's a good test. Okay. Or even better, like actually do the calculation. C++ can do it for you. Assert that that's actually equal to 42 plus 55, whatever that is. 42 plus 55. So that's a test. We can call it test calculator 1. We can make a test calculator 2 that actually like tests whether we can do 2 calculations one after the other, like it actually resets itself properly. Boop. Let's do, I don't know, 123 times 456. So now, if I press enter on this calculator, see, it should give me 123 times 456. Hopefully. And then I should also be allowed to do more calculations. I need to be able to press some more digits and actually like build up another number. So like, I don't know, C dot press digit 78, I don't know, 78, and then we'll subtract, press minus. 90. 78 minus 90. Why not? That needs to be the 0 digit. Okay, so this should give me back, if I actually run it now, pressing enter now, it should have reset itself. It should have performed 78 minus 90. And so you can make as many tests as you need to gain confidence that your calculator is working in the way that it should. And, well, hopefully, we have a bunch of past tests. Yay! So it sounds like we have a working calculator. Are there any questions about how I made the tests or anything else about this example? Definitely a more complicated, fun example. Go back and study it. It's a good one, I think. All right, so yeah, we modeled a calculator. How fun was that? 2 more slides for the day. I want to talk about pointers. That is, where is that? So I did make a little slide about this on the cheat sheet. So pointers, you use the star in a type that creates a pointer, star in a type, or ampersand in a type, remember that's a reference, not a pointer. It is address of, though. Ampersand is address of if you use it outside of a type, like this, p equals ampersand x. And then star outside of a type means dereference your pointer. Follow that pointer and get whatever was there. Okay? Remember that null pointer is just, it's like the 0 address, it doesn't exist, you should never dereference it. So, yeah, this example becomes this, like p equals the address of x. That means p holds the address 100. It also has its own address, we just don't think about it. So p points to x. If you say star p equals star p plus 1 now, it'll make the 42, 43, for example. Okay, so that's a nice color-coded pointer example, but let's do it in a bit more depth in a program. Let's see here. So a pointer. A pointer is just a variable. A pointer is just another box in memory, but the kind of thing that it holds is an address. The address of somebody else, or null. Okay? So pointer is a box in memory that holds addresses. Let's say if I have int x equals 42, I can make a pointer to x by making an int star y and have that hold the address of x. All right, so star is in the type for a pointer, ampersand outside of a type is for address of. Star in an expression does a dereference, so I could be like cout star y. Okay, so what this does is it hooks this up. It does, all right, it makes the x variable. Let's pretend that x lives at address 100. That's my silly favorite address. X holds 42. Once you say y in star y, that makes a new box in memory. Again, you have a place for y now. It has its own address. Maybe it lives at address 108 or something. Or if it's right after, it would be 104 technically. And you can set it to something. You can set it to the address of x, which means, all right, the address of x is 100. We're storing 100 in y, and that sets up this pointer relationship. Y points to x. And now when you say star y, it's going to follow the pointer, get the 42, and it will print 42 to the screen. Okay. Does that make sense? That's how it works. If you wanted to go even further, you can make a pointer to a pointer. So what is y but something with an address? So you can make a z. You can totally make a z that also gets its own address. Maybe it's it would have to be like 112 if we're in a 64-bit computer. That doesn't really matter. Have that hold the address of y, 104, and you can have it point to y, which points to x. And you have to dereference twice to get to the 42. So let me show you a bunch of those things, and then we'll go from there. So int x equals 42, int star y equals address of x. So now y points to x, and I can say, oops, y points to x. Y points to x. I can cout x. I can cout y, and y is a pointer, so I can follow it. I can say cout star y. Try and think about what all these things are going to print right now. And the types, they do have to align. If I'm trying to get the address of, if I'm trying to save the address of an integer variable somewhere, I need an int star. Y is a pointer to an int. It holds the address of an int variable only. The types have to align. All right, so x, of course, holds 42. Star y, because y is pointing at x, that also gives you 42. And then if you print y by itself, y is just a box holding a big number. It's an address. So here is apparently the address of x in this run of the program. It's different every time you rerun the program because your programs get loaded into different places. But yeah, that's just an address. But it always points to x. It holds the address of x. Okay? If you would like to make another one, make a pointer to y, think about what the types have to be. So z is let z hold the address of y. What does the type of z have to be? Well, it's a pointer to an int star because y is an int star. So it's int star. It has to be like that. Again, you can print just z. That's the address that it's holding, which is apparently the address of y. And then star z will give you whatever it's holding, which is y. It's a pointer to y. And you can say star z to get to follow the pointer. But once you get there, it was just y. Y is a pointer itself. Dereference that to get to x because y was pointing to x. So this is why it prints this. X is 42, y is an address. That's the address of x, because that's what y is holding. Star y follows that address to x itself, gets the value there. Z holds the address of y. This is the address of y in the program. Star z gives you follows the pointer, follows z to get to actually y. This gives you the value of y, which is that number, which is the address of x. If you dereference that thing, which was what z was pointing to, follow y, star that one more time, it gives you the value that y was pointing to, which is x. So that's the 42. One more time. Any questions about any of that? There's a lot going on, I know, but that's how it works. Remember your stars. Remember all the symbols. Try to keep them straight in your mind. Yeah, so this all just goes back to the idea of how memory works. So everything in memory is just a bunch of addresses mapping to values. this is what memory looks like. It's just a big table. Every address holds like a byte value. 0, 1, 2, 3, 4, 5, dot, 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 on and on forever. For example, 0 doesn't exist. That's the null pointer. You can't access that one. But everybody else does. If you wanted to store, like, an int at address 1, you could. Ints are 32 bits wide, so they would take up 4 addresses. But the starting address is 1. Okay? So you could store the int 42 there if you wanted to. Okay. That's the idea. So this is, I don't know, this is me holding a variable I at, which holds 42, starting at address 1, I guess. Okay? That's how it works. It would take up 4 addresses, 1, 2, 3, and 4. It's 32 bits long. 1 byte, 2 byte, 3 byte, 4 bytes. So, yeah, everything that has multiple bytes has that starting byte. And then for my final example, let me show you pointers to like some class or some struct. We can use vectors. So if I make a vector v, I can totally make a pointer to that vector. 1, 2, here's my vector v. I can make a vector pointer, vp, I guess, and that could hold the address of the vector v, and I could dereference it to get to the v itself and use its methods. Okay, so this is how you would declare vp. It's a vector int pointer, and you have to give it the address of v. And in order to like get at the size of the vector, to call a method on the vector itself, you have to dereference to actually get to that vector. So there needs to be a dereference and then a dot, or people have decided that that's silly and they gave you the arrow operator to do both for you at the same time. So that's the idea. So let's include the vector library. So vector int v equals 1, 2, 3. Vector int star vp. This now holds vp is able to hold the address of a vector of ints. Give it the address of v. Now we can actually dereference. We can go through vp. We dereference it. We can get to the vector and actually do the dot size if we wanted to. That'll give us back to 3. Or the same thing equivalent, we could have done vp arrow size. That's less parentheses to worry about. So either way, those will give me my 3s, and we are moving on. Any questions about that? So that's just pointers to classes or to structs. You have to like get to the actual thing before you use the dot. The arrow operator kind of is shorthand for that. All right, one last example. Let's go to the heap. Let's talk about the heap. So that's that magical place where you can store a bunch of stuff. A bunch of stuff dynamically allocated memory that lives for as long as you ask it to. It's not a local variable. It is dynamically allocated variable. So when you say new, you put a type after it, and then C++ will give you a brand new thing of that type made for you on the heap. And it tells you where it was with a pointer. It gives you back a pointer to that brand new thing. And then you can say delete to get rid of it when you're ready. You can wait to do that till the very end of the program or like in between some function calls. It will last as long as you want it to. So here's how you do it. You say like int star I equals new int. And you can set its value, of course, and be like star I equals 42. What that does is anything with a name is a local variable, first of all, unless it's a global variable defined outside of a class. So I is a local variable, but it's a pointer, it holds the address of something that got made all brand new on the heap, holding 42. So when we say new int, we go to the heap, C++ goes to the heap, makes a brand new box of that type. We ask for an int, so it gives me back a pointer to that brand new place that it made. And so I is set up like this, and it's now holding 42 once I give it a value. Once I'm done with it, like I can do it whatever I want. Once I'm done with that memory, I'd like to reclaim it so I can do other stuff on the heap later, save my memory. I'll say delete I, and that will remove this box, and then you should never use this pointer because it's pointing to freed memory. You don't want to ever touch that again. You could make arrays on the heap. It'd be like new int 42 or 24 or whatever with some brackets. But once you make arrays on the heap, you have to say delete bracket bracket so that you don't just accidentally delete just the first thing. No, that was an array that I allocated. Okay? Either way, you're getting back a pointer to the first element if you're making an array. Yeah, let's see. How do I want to explain memory leak? So the one thing that could go wrong is you lose that one pointer that was telling you where that thing was on the heap. That's called a memory leak, because now you're wasting memory on something that you can never access again. You have no way of reclaiming it. That's a memory leak. So let's say here's an example of a memory leak. Like you had your I, it was pointing to 42, everything was nice. You didn't delete it. Instead, you said right here, I equals new int once more. So what that does is it resets I, like chops off that. It makes a new box on the heap set to like question mark, and it points I there now. So you just leaked. You have no way now of accessing. You didn't remember this address. There's no way of re-getting it. So this is leaked memory. Let me write that better. Leaked. Does that make sense? You've lost a pointer to this thing. You have no way of getting to it now, which means you are now you're wasting 4 bytes of memory that you can never reclaim. All right. So what is the example that I want to do for this one? All right. Let's just do something simple like this example. Let's store a single integer on the heap, and we'll make it a bit more advanced. Okay. Int star I equals new int. So I points to an int on the heap now. And I can set it star I equals 42. See out star I. It's going to print 42. And then when I'm done with it, let's say that's all I needed to do, I can say delete I. And then I should never use that variable again. Or give it something else. It'd be nice if you just set it to null or something. That's a good strategy. So you can't accidentally access freed memory and get some random value. So this is printing 42 and gets rid of that int now. Does that make enough sense? So that's the first example. My next example, or I guess my last example for the day, is let's do this. Let's ask the user to give us a bunch of numbers and we'll save them in a heap array. So we originally, because it's the user telling us, we have no clue how big this array is going to be. So let's ask the user first for one number. That's the size of that array that they're going to build. So ask them for how many numbers are you going to type, user. So ask them for that. That's like our n variable or something. And then we'll make an array on the heap with that many numbers and fill it in with whatever the user gives us. And then we will calculate the median of that array. So this is a useful thing to do. And then we can delete the array because we're done after we've calculated the median. So that's one example, a real world example of wanting to save some memory away somewhere for just a little bit to do this calculation, get the median, and then we're done. We don't need it anymore. We don't need those numbers anymore. Okay, so let's ask the user to fill in a heap array for us. So I need to ask them first, how many things do you want to type? See out, enter the size of the array. Int size, let's get that. And now we have size. The user typed like 5. They want an array of size 5 or something. We can make that on the heap. Int star arr equals new int of whatever size that was. Okay, so this makes an arbitrarily sized array on the heap, and it gives us back a pointer to its beginning. Remember, that's how arrays work. Arrays are really just pointers to their beginnings. And you could still use r of 0 equals 42. You can use that notation. That's just doing pointer stuff, though. It's really doing star r. equals 42. Remember that? So we have an array now, and now let's fill it in. For int I equals 0, I is less than size, I plus plus. Let's fill in this array at each index. So see how it's asked the user for the next element. Enter the next element. Int next element. Cn next element. And let's put it now into r at I. Okay, so that's going to fill in this array with whatever the user types. And now let's calculate the median and give it back. Okay, so how do you calculate the median? Does anybody want to tell me? Do we remember? How do you calculate the median of some array? Let's say the user gave us 5 things and they were like, I don't know, 2, 1, 4, 3, 5. I don't know, something like that. That was the array that we got. How do we go about calculating the median of that array? Take the one in the middle. Could I just do this? Could I just give back 4? Is that the right answer? Yeah, so it needs to be in order, right? The user may have given us an unsorted array. Most likely they did. In order to find the median, we have to sort it. We have to sort it first. And the median will be the middle element at that point. So then we can make it 1, 2, 3, 4, 5. And then when we really go to the middle index, it's really giving us back the median. Okay? So that'll work. We'll figure out how to find the middle index. We'll calculate the median of the array by sorting it first. What happens if it's like this? Does anybody remember the median of this array? 1, 2, 3, 4? What's the correct median for an even-sized list of numbers? There is no real middle. What do you do? It's been too long. The last time I remember doing this was like middle school or like elementary school. So it's okay if we don't remember. But the idea is you take the two middle list things and you average them. So the answer is 2.5 for this example. You take these two middle things and average them together. So really the median, even if you're given an array of ints, the median can be a double. We must store the median as a double. So that's 2.5. Got to go in the middle there. There. Okay. So, okay. How do we sort stuff? Does our favorite... Oh gosh. Zoom, go away. Does our favorite website still not work? Darn. Alright. I have to learn how to use this other website. C++. Standard library. It's an algorithm where sort lives. And sort on an array works like this. You give it pointers. You give it a pointer to the starting thing, the starting element, and then one past the last element. Do they have an example? Yeah, this website's a little too fancy. It's using like C++ version 2020 and not using older stuff. So let me just show you how to use sort on this array. So first of all, if we want to calculate the median, double median has to be a double. Just in case we had an evenly sized array. So first we have to sort the array. Sort the array first. And you say sort. You use the algorithm library. You say sort, and you give it the address of the starting element. So that's just R. R itself is the address of the first element in the array. And then you give it the address of one past the end of the array, which is R plus its size. which is essentially because if you remember your, what's it called? If you remember your pointer arithmetic, r of 1, for example, the address of it, is equal to r plus 1. That's the syntax. Those are equivalent things. So, interesting. That's the idea. So if I want 1 past the end, it's r of size, because size minus 1 is the last element. R of size is, that address is 1 past the end. And that's what you give to sort the whole thing. And now it's sorted. Now we need to get the middle element. Okay? And the middle element is, well, there might be multiple, first of all. We have to figure out, like, is our array odd or even? What's the size? Is the size odd or is the size even? So if size mod 2 is 1, then it's odd. Right? There's 1 left over when you divide by 2. So odd size, middle index is, let's figure that out. So this is 0, 1, 2, 3, 4, and we want 2. So the size is 5. If you divide size by 2, you get 2.5. Integer division, that gives you 2. Okay, that works. So it looks like if you just divide by 2, it'll work out. Let's confirm that for some other sizes. Like, all right, if we have a size 3 array, it's 0, 1, 2. The size is 3 divided by 2, that's 1.5. Okay, chop off the 0.5, you get 1. So yeah, it looks like size over 2 will always give you the middle index. That's cool. Middle index is size over 2. So go there, that's the median. Int mid equals size over 2, median equals array of that middle index. Okay, that's the easy case. The other case is even size. So the middle indices are, there's 2 of them, what and what. So, okay, let's go back to this example. This was 0, 1, 2, 3. The size was 4. If we divide size over 2, it's even, we're going to get back 2. That is the right middle element. So if you do, it'll be size over 2 and then size over 2 minus 1 to get the 2 middle elements. Okay, that's the trick. So the middle indices are size over 2 and size over 2 minus 1. You don't need to put parentheses because of our rules, but you could if you wanted to. So those are the 2. So int mid right is, that index is size over 2, and then int mid left, that index is, well, it's mid right minus 1. That's how you can do it. And so the median, the correct median of an even-sized array is the array at the mid left, the left middle index, plus the right middle index over 2. And we want it to be a double because it's probably going to have a 0.5 in there somewhere, most likely. So we're going to divide by 2.0 so that we can do double division. And sorry, it's r of mid. And that's our correct median. So we can see out the median. But the idea is maybe you have a very long program that just needs to use the median to do a bunch of stuff. Just pretend there's a lot of stuff going on here. After we've calculated the median, we don't need the array anymore. Does that make sense? We have worked so hard to go through it, like sort it, do some stuff. But after that, this array is useless to us. We just wanted the median. Now we have it. It's saved safely away in the median variable. I can delete it. After we calculate the median, let's pretend, there's no more use for r. We are done with r. So let's delete it now. It's delete bracket bracket r, because it was an array. And now we can do whatever we need to do with our median that we calculated. We'll just print it out for fun. But imagine that you had a very long program down there. Oops. Let's do it this way. So let's do our first example. Out of order, 21435. Oh, sorry. First, the size is 5. 21435. And the median is correctly calculated to be 3. Yay. Let's do 1, 2, 3, 4. So it's size 4. 1, 2, 3, 4. It's already sorted. You're welcome. The median is 2.5. Cool. It looks like it's working just fine. So that is a, hopefully, non-trivial example of using the heap for something. You use the memory for as long as you need it. Once you're done with it, you can reclaim it so that you can use that memory for other stuff. Any questions about that example? Or anything else that we talked about today, because that was the last example. All right, so that is the end of the older stuff. Next time we'll come back and do like linear search, binary search, recursion, make files, all that fun stuff. We'll look at the cheat sheet some more, and we'll go from there. So that is all that I want to talk about today. Of course, there are no new assignments this week, but make sure to get everything in. One more review lecture, and then the final.